very happy to have our own Owen Lynch.
All right. I am giving a talk on composition of Port-Hamiltonian systems. This was my thesis topic at Utrecht University, and I was advised by John Baez and Violetta Russell. I'm going to start this talk by giving an outline so that you will know where you are and not get lost. I'm going to start out this talk by talking about effort and flow, which, well, I'm going to start with that, so I don't really need to just talk about it, what it is now. Dirac relations are, I'm just going to start with effort and flow, but I'm going to write this, I'm going to write down this so I can point to it during the talk. So 3 is Port-Hamiltonian systems. This is sort of the meat of the talk. 1 to 3, there will be 0 category theory. Maybe a little bit. I can't promise, but mostly no category theory. 4, also no category theory, but philosophy. So this is going to be ontology of relational composition. And then finally 5 is we're going to do 1 and 3, but this time with high heels and in category theory. So lax, symmetric, monoidal, pseudo functors. This is the framework of lax, symmetric, monoidal, pseudo functors. Say that 5 times fast. This framework is going to allow me to talk about 1 through 4 in category theory. Okay, let's talk about effort and flow. So we're going to start with a very simple setup. We have a space X. Let's say it's a manifold. It could also be a vector space. And then we have a differentiable function. H goes from X to R, which we call the Hamiltonian. And this Hamiltonian basically represents the energy of a system where the state space of the system is X. And let's suppose that we have a path through this system. So we have some time interval, I equals like A to B, and a path, gamma, going from I to X. Well, let's look at how H changes over this path. So H of B minus H of A, from the fundamental theorem of calculus, this is the integral from A to B of d dt H of gamma t dt. This is like the instantaneous change of energy. And now let's just look at this. Let's pull this out and look at this. D dt H of gamma t. Well, chain rule. This is the gradient of H, though we're doing differential geometry, so we're going to say the differential of H. Evaluated at the point gamma of t. And then we're going to dot that with gamma prime of t. except because this is differential geometry, we're going to say that this is like, this is not an inner product. This is an element of a dual space, and this is an element of a primal space, and we're just applying these. But we're going to use this notation in the talk. But yeah, this is basic, like lowbrow approach. This is just grad h dotted with gamma prime. Okay, now we're going to interpret this. This is all like quite simple math, but let's give an example of this and then try to name dh and gamma prime and see if we learn something. So our example, okay. Thanks, David. A traditional capacitor. So we have a capacitor here. What is the state space of the capacitor? Well, capacitors have charge on them. They have like charge building up on opposite plates. So the state of the capacitor is just the charge. So the state space is x equals the real numbers. And then the Hamiltonian of the capacitor is just h of q equals 1 over 2c q squared. I've made this mistake before. I hope that the c is in the denominator. Yes? Any electronical engineers who are going to call me out? Okay, good. No. So now let's apply this here. So let's suppose that q is a function of time. Q equals q of t. We're going to be a physicist here for a second because we're doing physics, so why not? And then we're going to say d dt h of q is grad h times q dot. And what is grad h here? Well, grad h is just 1 over c times q, and then q dot. So this is like dh. This is the derivative of gamma. This is also known as the current flowing into the inductor. The current flowing into the inductor is the change in the charge. This is the voltage. And from high school physics, the power is voltage times current. So this checks out. Oh. Okay. So the idea behind Port-Hamiltonian systems is that we always have two quantities. And these two there's lots of different domains in which there are two quantities. In the electrical domain, we have voltage and current. Their product is power. In a mechanical domain, we might have force and velocity. Their product is power. And a linear spring is exactly analogous to a capacitor when we just switch out voltage and current for force and velocity. We could also do a coil spring, in which case we have torque and angular velocity. But we could also flip these around. So this is where it starts to get a little tricky. So for an inductor, the state of the inductor is connected to the current going through it. So there's this property called inductance, and the current is a function of the inductance, and the voltage is the change in the inductance. And this analogy also works for the mechanical perspective. Sort of the dual of a spring is a particle. Particles store energy as like like particles have a state which is their speed, their velocity, and that changing that velocity requires energy, and that energy is supplied via force. Whereas as opposed to the state of a spring is a force, and changing that state requires velocity. And then gyroscope, like something spinning around, is that. So there are like, and in all of these cases, there's effort and flow. Effort and flow, effort and flow everywhere. Yes?
Would a capacitor be dual to an inductor?
Yes.
I'm just going to offer a suggestion. You might want to put those next to each other so it's easier to see the duality.
Okay, cool.
Thank you.
Yeah, so so this we have all of these similarities, and this points to a shift that we can make, where in engineering and physics we have a lot of different styles of diagrams, but they're all sort of kind of talking about the same thing. Like, these two systems are mathematically completely analogous, so let's use a notation that makes that clear. And this notation, this is something I came up inspired by a different notation, but that notation was kind of hard to make mathematically precise. So I made a different notation. I call this Dirac diagram notation. And the idea is you have like systems that can exchange energy, and they exchange energy through flows and efforts that travel along bonds that go between systems. And we'll see more about this in a bit. But so that's sort of an overview. Now I'm going to get back to the math. So let's just think about flows and efforts in isolation. So put aside the capacitor stuff. Capacitors are like energy storage. We're just going to think about energy on the move. In general, so this is sort of a one-dimensional example, but in general you could imagine a system might have several different ways of exchanging energy with its environment. So it might have several different efforts and flows. And the way we model that is by having a vector space V of efforts and a vector space, and then we consider its dual. No. Flows, efforts, yeah. We have a vector space of flows, and then its dual we consider to be the vector space of efforts. And we have a map like V cross V dual to R, which sends like a flow, effort and a flow to their pairing. So this is just the natural pairing between a vector space and its dual.
Is that a tensor, or?
This is just the Cartesian product.
Which is a function?
It's just a function, yeah. I mean, you can, if you make this a tensor, then this is a linear function. But yeah, it's just a function. And now if we're thinking about like flows traveling along a network, let's try to model this. So here we have like some schema of connecting something that has two electrical ports with something that has one electrical port. And Kirchhoff's current laws say that the two currents here have to add to the current here. And Kirchhoff's voltage laws, well, not even Kirchhoff's voltage laws, just the fact that voltage is the same across a short, means that the voltage across each of these dividers is the same. So we see we have this sort of funny thing, like there isn't a function that goes from the state of these ports to this, or the other way around. It's more that the flows and efforts here are related to the flows and efforts here. And this is how you would express this same thing in Dirac diagram notation. So what is this mathematically? Well, suppose we have flows and efforts okay, when we're talking about flows and efforts together, they're going to live in the vector space, which is this direct product. And now we want some like relation between flows and efforts over here and flows and efforts over here. So let's call this relation R. So what is R? Well, R is going to be, well, we want it to be linear because linear things are nice. So R is going to be a linear subspace of V direct product V dual, direct product W, direct product W dual. But not just any relation here is going to work. Because one thing that we want to be true is, well, we started with energy. We started thinking about energy. The whole point of flows and efforts is energy. We want this relation to preserve energy. So if you put in flows, if we have like if we have FV, EV, FW, EW in R, well, we want the power of FV and EV to be equal to the power of FW and EW. So we want EV, FV equals F equals EW, FW. And it turns out that we also, in almost every practical situation, I don't have a great explanation for why this is true, but in almost every practical situation, not only does the relation R satisfy this constraint, it is also maximal with respect to this constraint. So you can't add anything else to R without breaking this constraint. And you can prove that if a relation is maximal with respect to this constraint, then the dimension of the relation is half of the dimension of this whole space, and vice versa. If a relation satisfies this constraint and has dimension half of this space, then it is maximal. So if we look at this, relation again, the total space is 6-dimensional because we have 3 pairs of efforts and flows. And now the constrained space, well, we can choose V, we can choose V2, and we can choose I. This is what we were looking at before. We can choose I1 and I2 and V. This is sort of the dual situation where the current is the same throughout the whole thing, but now the voltages add up. And still here, we have the same thing here where it ends up being a 3-dimensional relation. And why are these power conserving? Well, basically, I times V1 plus I times V2 equals I times V1 plus V2. That's why. Yes?
What are the relations between right now? Are we comparing like one side of the diagram to another one?
Yes.
What are okay, in both this and the current example?
Yeah, so here V would be R2 and W would be R. So this is a relation between R2 direct product R2 dual, which is the space of which is the space of flows and efforts here, and then R cross R dual, which is the space of flows and efforts here.
Flow right now, voltage and effort is correct, or the other way around?
You could pick either one to be either one. Generally, the convention is that current is flow.
Okay.
Yeah. Good. Yeah. Okay. Cool. So yeah. So these are kind of dual. So and traditionally these are called zero junctions and one junctions. In Dirac notation, the way that this is represented is that the color on the outside of the junction adds, and the color on the inside of the junction is equated. So here, blue is on the outside. On this one, green is out on the outside. Okay. So that's Dirac relations. Okay, I said that there wouldn't be much category theory, but there's a little bit of category theory. Objects like this and Dirac relations between them form a category where relational composition is like normal relational composition.
Sorry, that preserves half-dimensionality?
It does preserve half-dimensionality, yeah. And this category also has some nice structure. It's symmetric monoidal with respect to direct product. But we'll get more into that here. So, okay, Dirac relations. Port-Hamiltonian systems. Oh, one more Dirac relation. This is a transformer. We turn a current of lambda I and a voltage of V into a current of I and a voltage of lambda V. This is also power conserving. I don't have a great Dirac diagram notation for this yet. If anyone has any ideas, hit me up. Okay, but now we're going to talk about Port-Hamiltonian systems. So a Port-Hamiltonian system is like a mechanical system or like a dynamical system that can exchange energy with its surroundings. So right here we have a pendulum. And a pendulum by itself doesn't just like a capacitor by itself. If you disconnect a capacitor from everything, it'll just not do anything. But if you disconnect this from everything, it'll swing. So there are some internal dynamics, but there are also external dynamics. So imagine here you have like a pendulum and a rope, and you can pull on the pendulum and speed up the pendulum. So you're putting energy into that system by exerting force at a certain velocity. You're doing work on the system. And what does that look like? Well, we start exactly like this. Actually, oops, wrong side of the eraser. We have a manifold. We have a Hamiltonian on that manifold. And then the last thing is somewhat more complicated, but we have an interface V. So in this case, V would just be R. So like we have an interface of flows and efforts. And then for every x in X, we have a Dirac relation D, which goes from the tangent space at X, direct sum the cotangent space at X, to V dual.
Can you use like a bar through the arrow?
The bar through the arrow means that it's a relation. Yeah, and specifically here a Dirac. So it's a relation that is power conserving and is of dimension half the space. Yeah, so it's called a Dirac relation. So D is a Dirac, really it should be D sub X is a Dirac relation, because yeah. Yeah, and there's some smooth, like d sub x should depend smoothly on x, but we're not going to worry about that right now.
Is that ever a problem in practice?
Not yet. I mean, I haven't gotten very, actually, yeah, I mean, there's a bit of an ugly bit in my thesis where I can't prove that something preserves the smoothness, so I just don't assume a smoothness. And for what I am doing, I don't need the smoothness yet. Once I want to start proving more interesting things, I will almost certainly need the smoothness. Okay, so so what does this mean? Well, what does this mean? In order to say what this means, we're going to talk about what the behaviors of this system are. A behavior on a time interval I equals A, B is a path. So gamma goes from I to X. Also a path through the interface. So F goes from I to V. E goes from I to V star. So flows and efforts that are also happening such that for all t, we have that gamma prime of t dh sub gamma t f of t e of t is in d sub gamma of t. So what does this mean? Well, it means that the flows through the interface are related to the flows in X. And what we can derive from this is that from this property of Dirac relations, we have gamma prime of t dh gamma of t is equal to f of t e of t. So by what we said at the beginning, but when at the beginning we integrated this from A to B and we got the change in H. But these are equal. So we can integrate A to B f of t e of t dt equals h of b minus h of a. So the change in the energy of the system can be determined by just looking at what is passing into the system on the interface. This is a statement of the first law of thermodynamics that energy is conserved. Okay, let's talk about examples. So in this example, we have basically, so we have a motor here. This motor has no state. So X is just like a one element set. And essentially all this is doing is this is a relationship between V and I and tau and omega. And basically, it acts like a transformer, except a transformer that goes between unit types. Well, there are no units in this framework, so mathematically it's the same thing. But like, we're doing a power preserving. We're like, for instance, I actually don't know how motors work. I don't know if motors are like voltage driven or current driven. But one way it could work is that tau is a multiple of v, and that I is a multiple of omega, for instance. And then here's a flywheel. The flywheel acts like a capacitor. Or more specifically, it kind of acts like, if you think of rotational velocity as current, it acts like an inductor in that its state is kind of the speed that it's, the angular velocity that it's going at. And then you can apply torque to it to increase or decrease the speed. Increase or decrease the velocity. And this is a zero junction. Well, I don't know if it's a zero junction or one junction, whatever. My notation is more clear than 0 or 1. The blue things all have to be the same. So this is like all of these axles are on the same. These are all on the same axle, so all of their rotational velocities have to be the same.
Oh, sorry.
Very low latency. There we go.
And then the torques all add up. Yeah. Oh, one thing I didn't explain about this notation. So, right, so there are two dots for a junction. It's the greens, or whatever the outside color, so in this case the torques. The torques on this add to the torques on this. So there's always a directionality to bonds. Bonds go from dark to filled in. Yes?
Which parts of these notation are doing work? There's color, there's filled in versus not filled in, there's connectedness between boxes, there's like equations that are written in here, like which things are supposed to be derived?
They're redundant. They're all redundant.
Which things are redundant?
Like,
Derive the equation.
yeah, you could, right. So like, these labelings are totally redundant with the diagram. Like, you could completely lose the diagram and just have these labelings, because like this is saying that all of these are the same and then the torques add up. But like, it's like the labelings are meant to help you understand the diagram.
Okay.
Yeah. That make sense? Yeah? No?
And filled in dot versus not filled in dot?
That's the directionality of the bond. So the filled in dot versus not filled in dot is redundant with the arrow. Yeah. So it always goes from, yeah. Because it's like it means that power is traveling. It means that this product represents power going from here to here. So when this is positive, power is going in this direction. So yeah, so if like current is negative and this is positive, then power could be going in this direction. It's not necessarily only going in one way, but it's sort of giving a convention. Yes?
So to know how much the motor is affecting the flywheel, we have to know what's happening on the outside board of this box.
To know how much the motor is affecting the flywheel. Your question assumes cause and effect. There is no cause and effect. There is just admissible behaviors.
Well, there's a change in Hamiltonian with respect to time. There's the movement through the X and stuff like that.
Yeah,
right?
but like they're like, it's not necessarily unique. It doesn't necessarily exist. Like, you could have, if you like assume that there are certain flows and efforts here, there may be several dynamics inside here that are compatible with that. There may be none. Yeah. Yeah, it's relational. It's relational. Okay. Okay, I'm going to give a couple examples, and then we're going to move to philosophy. So here is another example. As you can tell, I'm not a mechanical engineer, but this is what I think a hover car might be. You have like the hover car has like some mass, and it's like going in a direction, and then you have two fans on it. So this fan sort of blows it forward and back, and this fan turns it. And you can represent this, again, with this Dirac diagram. So we have a wire coming in to each of the fans, and that's sort of converting electricity into, this is like converting electricity into X force. Here, now we have like vector valued bonds. And here we have Y force, and then these forces are acting on the chassis, and the chassis is like has a position and a velocity and is moving around. So, stuff happening. So now I am going to talk about philosophy and then category theory. So this is sort of the ontology that I've come up to express these systems. And there are four things in the ontology. There are systems. Systems are kind of at the center, but systems have interfaces. So here in this Port-Hamiltonian system, it has an interface that it outputs and receives power through.
Each system has one interface.
Each system has one interface, yes. Then there are links between interfaces. So these are the Dirac relations. Each link relates to interfaces. And then we can use links to compose systems, which we'll talk about in a bit. We've already sort of seen that. So here, like, these are like descriptions of Dirac diagrams, and we've shown how we can use these to compose these systems sort of in a sketchy way, but we're going to talk about that more precisely. And finally, systems constrain behaviors. So they're like, a system says, okay, of this space of possible behaviors, I can only do these things. But it doesn't necessarily say, like, oh, if I'm at this state at time t, what am I going to be at in time t plus 1? That's not how these systems work. Okay. That's the ontology. Now, lax-symmetric monoidal pseudofunctors. Oh, geez. Okay, so I have 10 minutes. I hope that if the category theory does not appeal to you, then you have at least learned something before the category theory happened. I won't erase that yet. Okay. So, lax-symmetric monoidal pseudofunctors. They're not as scary as they seem. They're kind of nice. But so we start with a category, Dirac rel. This category has as objects the objects, vector spaces, the morphisms are relations, Dirac relations, we'll say R, which go from like V dual, W dual. Composition of relations, let's write this out explicitly, because not everyone has seen it. S compose R equals, like if S goes from, if like, so we have R here, we have S goes from W dual, give me another letter, X, great. S compose R is like the S compose R is the set of, I'm going to say V and X, where V is from this big thing and X is from that big thing, such that there exists W with VW in R and WX in S. As David said before, it's not trivial that this would be linear or preserve power. Or, well, actually, it makes sense that this preserves power. Because if, like, we have this equality and then this equality, then we have this equality. If that makes sense. But then the half-dimensionality constraint, that's not trivial to prove, but it's true. Strange, but true. Okay, so this is a category. It's a nice category. We can now put a symmetric monoidal structure on this category. Given by just direct product. So direct product goes from Dirac rel times Dirac rel Dirac rel, and basically like V1, V2 get mapped to V1 tensor, or not tensor, direct product V2. And then if we have like V1 direct product V star R1 V W1 da 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 da. Basically, you can just take R1 direct sum R2, because remember these are like these are subspaces, so we can take their direct product as subspaces and get a subspace of the direct products. You have to sort of switch things around, but anyway, it makes sense, and it's sort of independent composition of relations. And what does this mean in practice? Well, this means, this symmetric monoidal structure means that you can take interfaces. Like if I have some, diagram up here that relates these interfaces, and I have some diagram here that relates these interfaces, well, I can just say that it's a diagram between this and this. Yeah. This is why we like symmetric monoidal categories in applied category theory. So what's the next ingredient? This next ingredient I named specially to annoy chemists. We have a functor pH going from Dirac rel to cat. And pH of V is the category of Port-Hamiltonian systems with interface V. I'm not going to tell you what the morphisms are because we're running out of time. But yeah, category of pH systems on interface V. And yeah, it's this thing. No, shoot, it was on here, but it was a manifold, a Hamiltonian, and a relation between the tensor product and the tensor. No, not the tensor. The tangent space and its dual with the interface. Yeah. And okay, the PHV. Question. Well, one question. What does this do on morphisms? So, if we have like V direct product V star and R W product W star. Well, how do we take a Port-Hamiltonian system on V direct product V star and make it a Port-Hamiltonian system on W direct product W star? Well, Port-Hamiltonian system X H D gets mapped to X H and then what I'm going to call R lower star D, where R lower star D sub X, well, what does this need to be? Well, it needs to be a relation between Tx direct product T star X and V product V star W, yes, thank you. And, well, we have a relation from this to V, and we have a relation from V to this, so we just compose them. So this is equal to R compose D sub X. So the action of this functor on morphisms is pretty simple. And now the really fun part is the lax symmetric monoidal part. So what does this mean? Well, really it all comes down to one natural transformation. And then there's like a bunch of coherences and equalities around that. But fundamentally, the meat of the whole lax symmetric monoidal pseudo bit is a natural transformation PHV times PH W to PH V direct sum W. So we want to take a Port-Hamiltonian system on V and a Port-Hamiltonian system on W and create a Port-Hamiltonian system on V direct sum W. And the idea behind this is that this is just like independent. We're going to like take these two Port-Hamiltonian systems and then we're going to put them together, but they're not going to interact. We're just going to let them do their own thing. So we're going to take X H sub X D, I have to use a superscript X here, and Y H Y D Y And this is just going to map to, well, we're going to take the Cartesian product of x and y. And like this, that makes sense. The state space of the two systems independently is just, well, you have a state in one and a state in the other. Then the energies just add up. So it's going to be h sub x plus h sub y. And then finally, we're just going, these relations, well, we're just going to use this tensor product, this direct product of relations. So we're just going to have dx, sorry, dy. And this sort of gives us a general formula. With this and this, we now can compose multiple systems and actually have them interact.
No idea.
There you go.
Do you need it?
Um,
Showing up.
oh well. What? Oh yeah, maybe. Oh, there we go. Oh. It is on. Okay. There we go. So if we go back here, well, how do we interpret this categorically? Well, the first thing that we do is we take these three systems and we compose them independently. So you can sort of extend this to 3 rather than 2. And so we get X fan body and Y fan just sort of all doing their own thing. And then we take the relation between all of the sort of internal flows and efforts and flows here and the external efforts and flows. So this and this. And when we turn this from a Port-Hamiltonian system on like these efforts and flows to a Port-Hamiltonian system on these efforts and flows by applying that relation. Yeah, I don't really have time to talk about behaviors categorically, so I think I'm going to end here and have questions. Yes.
So you use circuits in a lot of your examples.
Mm-hmm.
Once upon a time, I was thinking about circuits, and I came across some stuff that I think maybe was due to Dirac. So that might be why his name is associated with all your work. But
Due to who?
Dirac.
Oh, Dirac.
Yeah.
Okay.
So there's a way to there's a Hopf algebraic structure you can put on like circuit diagrams, and also like a way to organize them using operands, where then like writing down the differential equation that dictates the behavior of the circuit is just some algebraic thing. I was wondering if you came across that or in your studies, and if so, how it fits in or relates to this. It sounds like you're doing something more general, but are you familiar with this?
No, I'm not.
Okay.
So I'll say two things. So one, Dirac relations is not a standard term in the literature. People normally talk about Dirac structures, which are sort of like Dirac structures are just on this. So it's just talking about the subspace rather than like the whole thing. So Dirac structures could very well come from that. I don't know. I don't really know the etymology. Second thing is that we have here in our audience someone who did his thesis on electrical circuits categorically. Did you ever read this Hopf algebra stuff?
By Hopf algebra, would you call it a bialgebra or something like binomial?
It is a bialgebra with an extra
Yeah, with
property,
extra-
but
extra
I don't think it's
interesting.
terribly important in this setting. I think it kind of comes along for the
Yeah.
ride. So if there was a way that you were thinking about with bialgebra, those probably.
I've thought about some of this stuff. I've never written any of it down.
I feel like I
That's
maybe
what
I learned this from a blog post of John's. So So maybe.
Okay, well, I will say, so there's a, on Dirac there's a natural, I think there on every object of Dirac there is a natural Hopf algebra structure, I believe. Because, yeah, you have monoid, you have the monoidal structure is like, well, actually, yeah, no, in fact, you have two, because zero junctions and one junctions, like zero junctions form a Frobenius algebra, one junctions also form a Frobenius algebra, and then you have like transformers, which is like scalar multiplication. So I don't know if that all adds up into a Hopf algebra, but yeah.
Yeah, it gives a Hopf algebra structure.
Okay. Yeah.
There's all sorts of fun games you can play with, and various building constructions too. Get to like deformed type structures.
Yeah, I looked at this, but it didn't actually end up making its way into my thesis because I didn't end up having enough time.
Yeah, I mean, I think what you're doing, it seems much more general, but maybe like sitting inside there, this very old story that is
Well,
not as modern as the way you think about it.
In a sense, I am sort of just doing electrical circuits.
Yeah.
It just turns out that everything else is also electrical circuits. More questions?
So what's the role of plus and duplicate? Why is plus and duplicate happening so much here and not really written there? Is it like this half-dimensionality thing, or?
What do you mean? What's the
Plus
rule?
and duplicate are happening all over the place in your pictures. With,
Oh,
with
so
like inside and outside and stuff like that.
so
circles.
like, yeah, the inside and outside circles, those are specific examples of Dirac relations.
So it's just that all of your examples come from a subcategory of Dirac relations.
That are using plus. And yeah, I mean, it turns out, in a sense, just like you can sort of, like, linrel, you can take linrel and generate it with like plus and copy and scalars. I think you can also do that with Dirac rel. So in a sense, that's sort of all you need. Yeah, but this is like the analytical way of, so you could maybe do it like combinatorially with like some combinatorial wiring diagram things that have, yeah, I'd be interested in like giving a like I don't have a combinatorial structure for Dirac diagrams yet. I just haven't sat down and figured out what it would be.
Yeah, like it should be this kind of like Hopf algebra type gadget.
Yeah.
Where like the elements are sort of generated by basic building blocks, and those basic building blocks are like these pieces of your Dirac diagram.
Right.
Like
Yeah.
roughly speaking.
Yeah. I mean, the question I have is like, so you've got this sort of combinatorial syntax, which is built on like physically wiring things together.
Mhm.
And in some sense, everything you want to express
Too late.
Can be expressed through these combinatorial generators because you're trying to mimic combinatorial physical situation.
Mm-hmm.
But does that give a full presentation of the Swiss semantics you're interested in here? Or so you kind of suggested it was. No, it did. But I'm not sure that it, well, I haven't.
I think it does. I don't know how much I care. I don't know. It's an interesting question to look
And
at.
then the question is the gap even interesting? Right?
Yeah.
Maybe if you can't express everything, well, it doesn't matter.
Well, okay. So one thing that I do care about is, so these are all like linear relations, and in a sense, like these interfaces sort of don't depend on the state that each system is in. The relation between the interface and the system does depend on the state of the system, but the interface itself is like, you could think of it like a trivial vector bundle. And if you're thinking about like systems with complicated, like mechanical systems with complicated geometry, then you may end up with non-trivial like vector bundles, which is studied in the Port-Hamiltonian literature, but not modeled so well by this framework. And I'm not quite sure how to do that yet, because it's like, if the interface depends on the system, well, then it's kind of weird to have like right here I'm having a functor from interfaces to categories of systems. So it's just, yeah. So I don't know how to do that, but that is like something that is interesting. I mean, there's also like, there's another type of composition of systems, which is like more about gluing. This is composition of, the systems always stay separate. You never end up gluing things, but you let them talk to each other. So there might be another composition where you like actually glue the system somehow. Like if you have mechanical systems. Yeah, I don't know. Like adding constraints. I mean, this is already sort of constraints. I don't know. Yeah. Yes.
So in these Dirac diagrams, I'm seeing we've got some sort of dots and ports with various decorations. We've got these lines with the arrows. We have some colors on either side of them. Maybe this is a reach, but are these meant to be string diagrams for some kind of two-dimensional structure, like a double category?
So, no. Short answer, no. So definitely there's no, the only two-dimensionality here comes from the monoidal structure. There is a double category theory picture on that, but the double category theory, the extra dimension that the double category theory adds is a dimension of maps between systems, of morphisms between systems, not additional structure here. So this is implicitly a string diagram. It's a string diagram where the domain is all of the inside ports and the codomain is all of the outside ports. So really what this picture is this picture is turning a symmetric monoidal category into an operad. So like this is an element that, if you forget about the things on the inside here, this is an element of the operad of the symmetric monoidal category, of the operad that comes from the symmetric monoidal category Dirac rel.
Great. While we're on double categories, are you in the business of applying the decorated cospan construction to this lax monoidal functor? So my advisor for this was John Baez, and yeah, John Baez likes decorated cospans, and this seems really kind of to be a different use for lax monoidal functors. Yeah, it's like this like style of using lax symmetric monoidal functors started with an earlier paper of mine for thermostatics, and we were like thinking like as soon as John Baez saw like the lax symmetric monoidal functor, he was like, decorated cospands, and then it like didn't quite work. It like didn't make sense. Part of
So
why I ask is because at the end, when you described how you sort of compose these three things by kind of doing them independently and then adding in the relations, somehow, that feels very much like composition of decorated cospan.
No, it does. You're right. Yeah. So I don't know what the exact relation is. Yeah.
Thanks.
Yes.
I guess one question is just like, where is this, how necessary is this like linearity and like vector space stuff to this story, right? Like, I'm just like, I guess I'm having trouble seeing like where it comes up and ties things together, right? And I guess, right, like, sort of building on that, like, can you, I guess my physics isn't that great, right? Like, could you model like more discrete systems like that kind of like still sort of like preserve some kind of like energy like quality with this, or like where does that break down?
Well, so let's see. So one thing is that if you're talking about power and you want to talk about energy, power is instantaneous flow of energy. So you kind of do need to be talking about differentials there. In terms of the linearity here, Pretty much like, yeah, I don't even know what structure. It would just be like, first of all of the important examples are linear here. Notice that there is nonlinearity that shows up in the relation of D on X. That is nonlinear. So that allows you to do interesting things like, for instance, rotations in 3 dimensions. That's like one thing that is like classically very well treated by not having to deal with coordinates and instead doing like a manifold like SO3. Like you can work with like a manifold SO3 and think about rotations. And then, so that's like very nonlinear. And if you want, and then if you want to think about like a rigid body with like forces acting on it, then this d sub x is like really going to depend nonlinearly on x. Notice for a capacitor, it doesn't depend on x. I didn't say that explicitly, but yeah, it doesn't depend on x. But for like when you have like rotations and stuff, or a pendulum, for the pendulum, like the angle of the pendulum is going to change how your force, if you have a linear force, how it's affecting the pendulum. Like there's a degenerate case where when the pendulum is like totally out straight, you can't pull on it at all. So that's like suddenly that's like a singularity in d sub x. So yeah. So there is stuff like that going on, but yeah, generally in differential geometry, you like let all of your nonlinearity happen in the manifold, and then in your vector bundles, you have everything be linear.